All right, this question will be going over the Sapling 5.1. Follow along if you need some help. All right, question one. If Aaron tunes into his favorite radio station at a randomly selected time, there is a 20% probability that a commercial will be playing. Interpret this as a long-run relative frequency. So if he did it many, many times, probability would be about 20%. Let's see which one comes closest to that. If Aaron tunes into this station at 5 randomly selected times, it would be exactly 1 time. We know that's not true. Aaron listens to his favorite radio station for 100 minutes, and 20 of those minutes will be commercials. No, that's not also true. We're looking for more of an approximate thing. So if you look at the last one, if you take a very large random sample of times that Aaron tunes into his favorite radio station, about 20% of the time a commercial will be playing. And that's a little bit more on par with the description. So we're going to pick that one. Number 2, Aaron tunes into his favorite radio station at a randomly selected time. There is a 20% probability that a commercial will be playing. Now, if Aaron tunes into this station at 5 randomly selected times, will there be exactly 1 time when a commercial is playing? And the answer, of course, is no, because it could be none of the times. What if all the randomly selected times were in the same commercial block? Then you wouldn't have it. You would have all commercials, right? So answer is no. If Aaron tunes into the station at 5 randomly selected times, there will not necessarily be exactly 1 time when a commercial is playing. That seems pretty appropriate. Let's look at the other no's. If Aaron tunes into the station at 5 randomly selected times, there'll be at least 1 time when a commercial is playing. And then we don't know that. And there is no way to predict how likely it is that a commercial will be playing when Aaron tunes into a radio station. Well, that's not true either. There is a way to predict. It's what our probability is. So it's going to be this one. It could be more than 1, less than 1, but there will not necessarily be exactly 1 time. All right, question 3. Many women choose to have annual mammograms to screen for breast cancer. After age 40, a mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. False positive. Other times the test says that a woman doesn't have breast cancer when she actually does. False negative. Suppose the false negative rate for a mammogram is 10%. What does this mean? The mammogram is accurate 90% of the time. The mammogram is inaccurate 10% of the time. Well, those are not true statements. If you take a very large random sample of women without breast cancer, about 10% of the time the mammograms will indicate that the woman has breast cancer, when in fact she does not have breast cancer. So false negative is 10%. False negative is a woman doesn't have breast cancer when she actually does. 10% of the times the mammogram will indicate the woman has breast cancer when she does not actually have breast cancer, which is the opposite. So that's no good. So if you take a very large random sample of a woman with breast cancer, about 10% of the time the mammogram will indicate the woman does not have breast cancer when she in fact does. Should be that one. Okay, question 4, same scenario. What is more serious in this case, false positive or false negative? Well, I would argue that not knowing that you have cancer is probably worse because you're not getting treatment. So I would say this case when a woman doesn't have or doesn't, the test doesn't say she has breast cancer when she actually does, a false negative would be more serious. So a false negative because a woman with breast cancer will not get potentially life-saving treatment. She might die because she's not getting treated. So I would say that's more serious. And the book agrees. Okay, number 5. The figure shows the results of a basketball player attempting many three-point shots. Explain why this graph tells you about chance behavior in the short run and long run. Well, in the short run, it's very unpredictable. As you can see, it's kind of all over, but eventually it's going to kind of level off to what appears to be 30% or something like that. So in the short run, there was quite a bit of variability in the percentage. However, in the percentage made free throws became less variable and approached 30% as the number of shots increased. That seems appropriate. Let's look at the other options. As the number of shots thrown increases, the percentage of made throws becomes less variable and approaches 30%. See, these are pretty much the same, but this one here talks about the short run. So that's the more complete answer. A gambler knows that red and black are equally likely to occur on a spin of a roulette wheel, number 6. He observes that 5 consecutive reds have occurred and bets heavily on black at the next spin. Asked why, he explains that black is due. There's no such thing as you're due for something, so that's going to be incorrect. So the incorrect ones, if 5 reds occurred in a row, reds are more likely to occur than black, so he should always bet on red. Well, if they're equal, then that's not the case. There is also green on the roulette wheel, which hasn't come up in the last 5 spins, so green is due. That's not true. The wheel is not affected by its past outcome. It has no memory. It's the last one. All right, number 7. A gambler knows that red and black are equally likely to occur on each spin of a roulette wheel. He observes that 5 consecutive reds have occurred and bets heavily on black at the next spin. That's why he explains that black is due. After hearing you explain, oh, this is the same problem. I don't know why I'm reading it again. After hearing you explain why red and black are still equally likely after 5 reds in the roulette wheel, the gambler moves to a card game. Different scenario. He is dealt 5 straight red cards from a standard deck with 26 cards, 26 red cards, 26 black cards. He remembers that you explained about roulette and assumes the next card dealt in the same hand is equally likely to be red or black. Anyway, is the gambler's reasoning about the card game correct or incorrect? What's his reasoning? He remembers what you explained about roulette and assumes the next card dealt in the hand will be equally likely to be red or black. Well, if you're dealing the cards, then you're going to be one less card before. So the probabilities are going to change, right? Removing a card changes the composition of the remaining deck. If you hold 5 red cards, the deck now has 5 fewer red cards because you're not replacing those cards. So it's going to be answer choice C. Question number 8. Luke's teacher has assigned each student in his class an online quiz, which is made up of 10 multiple choice questions with 4 options each. Luke hasn't been paying attention in class and has to guess on each option. However, his teacher allows each student to take the quiz 3 times and will record the highest of the 3 scores. Passing score is 6 or more correct out of 10. We want to perform a simulation to estimate the score that Luke will earn on the quiz if he guesses at random all the questions. Following steps describe how to use a random number generator to perform one trial of the simulation. Let 1 be guessed correctly. Let 2, 3, 4, 5 guessed incorrectly. Generate 10 random integers from 1 to 5. Simulate the results of Luke's guess for each of the 10 questions. Record the number of guesses and repeat this 3 times and record the highest of the 3 scores. So there are some mistakes here. First thing that you should be able to notice is that there are 4 options. So the probability is not 1/5, it's 1/4. So we don't want this to be, 1 and then 4 others. We'd want this to just be 3 others. So 1 out of 4. So we don't want to generate the numbers 1 through 5. We want to generate the numbers 1 through 4 to simulate the results. We're still going to draw 10 because we're doing 10 questions. So we want them to be 10 integers. But it's going to be step 1 and step 2 in this kind of scenario. So there are only 4 answer choices. So we want 2, 3, and 4 to be incorrect. 1 to 4. All right, let's do the next question. Clear this stuff out. All right, Luke's teacher has assigned each student in his class an online quiz. Same scenario. We have 50 trials in this simulation, which is not a correct interpretation of the dot at 1. So what each dot represents is 10 simulated quiz numbers being chosen. So one simulated quiz, and then the one and that one dot means on that simulated quiz, he got 1 out of 10 correct. He didn't actually take the quiz and get 1 out of 10 correct. It's just that would be that simulation. So what's not a correct interpretation? So Luke earned a 10% on his quiz one time. Now, this is not a quiz. This is a simulated quiz. So this is actually the right answer because that's not correct. There was one trial in the simulation that resulted in a quiz score of 1 out of 10. That's correct. 2% of the trials resulted in a simulated quiz score of 10%. Well, that's 1 dot out of 50, which is 0.02. So that is 2%. 2% of the simulated quiz scores, again, simulated, resulted in Luke earning a 1 response out of 10. Again, 1 dot out of 50 is 2%. So that is also true. And 1 of the 50 trials in the simulation resulted in a quiz score of 10%. That is also true. So this is the only one that did not happen because this is not an actual quiz, okay? He didn't take the quiz. This is a simulated process. So it's going to be this one. All right, same scenario. Use the results of the simulation to estimate the probability that Luke passes the quiz. So passes the quiz would be 6 or more. So since 6 or more would be over here, there's 1, 2, 3, 4, 5, and there's 50. So I would say 5 out of the 50 times he passed the quiz. That's, of course, 1 out of 10, which is 10%. So the estimate of the probability he passes the quiz would be 10% based on this simulation. If Doug scored 8 points on the quiz, this is question 11, is there convincing evidence he understands some of the material? Why or why not? Well, let's see. If Doug scored 8 points on the quiz, 8's all the way out here, right? There is no simulated dots that got 8 out of 10 correct. So the probability of getting 8 or more is equal to 0 out of 50. In other words, it is super unlikely to get 8 or more on this quiz. So I would say that Doug kind of knows what he's doing, right? So Doug, smart. He understands. Yes, Doug got 8 out of 10 because he has the highest. He doesn't necessarily have the highest score in the class. We don't know that. But it is unlikely that Doug would score higher than 6 out of 10 based upon randomly guessing. It's pretty hard to get 8 out of 10 randomly guessing. So since he did score 8 out of 10, there's reason to believe that Doug does understand some of the material. Doug is good. He knows what he's doing. It's this one here. Okay, question 12. The Transportation Secretary Administration is responsible for safety in the airports. Some flights, TSA officers randomly select passengers for an extra security check prior to boarding. One such flight had 76 passengers, 12 in first class, 64 in coach class. Some passengers were surprised when none of the 10 passengers chosen for screening were seated in first class. Shocking. We want to perform a simulation to estimate the probability that no first class passengers would be chosen in a truly random selection. So let's look at how we'd simulate this. We got 76 passengers, 12 of which are in first class. This right here is what we're going to use to like make our comparison at the end. So we're not worried about that yet. Okay. we want to simulate this probability. The probability that no first-class passengers would be chosen. So if we look at our first-class passengers, we got 12 of them, and there's 76 total. So the probability of being chosen in first class is equal to 12 out of 76. So we want 12 numbers to represent first class. And then we want 76 minus 12, which is what's that can be 64, to be not first class. So how do we simulate that? Well, there's a couple different options here. Number of the first class passengers 0, 1 to 12, and the other 13 to 76. Ignore all other numbers. Moving left to right, across the row, look at pairs of digits until you have 10 unique numbers, no repetitions, because you do not want to select the same person twice. That's true. Count the number of two-digit numbers between 0, 1, and 12. Perform many trials of the simulation. Determine what percent of the trials showed no first-class passengers selected for screening. That seems plausible. Let's look at the next one. Number of the first-class passengers 1 to 12, 13 through 76 for the others. Ignore repeats. Moving left to right, look at pairs of digits until you have 10 unique numbers, no repetitions. Count the number of two-digit numbers between 1 and 12. Determine how many first-class passengers should have been selected for screening. Notice we're missing this. We want to be able to do that many times, so we got to have that. The third one, number of the first-class passengers 1 to 12, 13 to 76 for the others. Look at pairs of digits until you have 10 numbers. You got to have unique. So that's no good. And the last one, number of the first class passengers 1 to 12, the other one's 13 to 76. Ignore all of the numbers, moving left to right. Look until you have 10 unique numbers, no repetitions. Count the numbers of numbers between 1 and 12. Perform many trials, determine what percent of the trials showed no first class passengers. This is good and all. The only problem is you don't have the 0. All right, you need that 0 there for a table. Table has two-digit numbers. So we can't choose that one. So it's going to be this one right there. Let me make this a little bit smaller. There we go. All right, so here's a simulated trial. We do not want to select the same person twice. Let's see if we can come up with our digits. So we're looking for the number of two-digit numbers between 0, 1, and 1, 2. So 71's no good, 48's no good, 70 is no good, no 99's, no 84's, no 29's, 07. That's going to be your first one. Now, how many did I have? We have 1, 2, 3, 4, 5, 6, 7. Those are no good. 8, 9, and 10. So out of those 10 numbers, only one of them was between 1 and 12. So it should be just the third option, 7. All right, number 14. In 15 of the 100 trials of the simulation, none of the 10 passengers chosen was seated in first class. Does this provide convincing evidence that the TSA officers did not carry out a truly random selection? Well, what's 15 out of 100? Well, that's going to be what? 15%? That's pretty high. So I would say no, it does not provide convincing evidence. There is not convincing evidence that the TSA officers did not carry out a true random selection. If the selection is truly random, there's about a 15% chance that no one in first class will be selected. All right, question 15. A media report claims that 50% of U.S. teens The smartphones feel addicted to their devices. Skeptical researcher believes that this figure is too high. She decides to test the claim by taking a random sample of 100 U.S. teens who have smartphones. Only 40 in the teens in the sample feel addicted to their devices. Are you addicted to your phone? I probably am. Does this result give convincing evidence that the media report's 50% claim is too high? To find out, we want to perform a simulation to estimate the probability of getting 40 or fewer teens who feel addicted to their devices in a random sample of 100 from a very large population of teens with smartphones, in which 50% feel addicted. So we want to simulate 50%. So we can do that a number of ways. We can flip a coin. We can do a random numbers. So in this case here, 1 feels addicted, 2 does not feel addicted. Use a random number generator to produce 100 random integers from 1 to 2. Record the number of ones. Repeat this process many, many times. Find the percent of trials on which the number of ones was 40 or less. So will this give us 50%? I believe it will, because you have 2 numbers. So the probability of you getting one of those numbers in the long run is going to be 50%. So it is a valid simulation design. By letting 1 equals feel addicted and 2 does not feel addicted, the simulation would model a 50% claim. "16. Do most teens recycle? To find out, an AP Stats class asked an SRS of 100 students at their school whether they regularly recycle. In the sample, 55 students said that they recycle. Is this convincing evidence that more than half the students at the school would say they regularly recycle? The dot plot shows the results of taking 200 SRSs of 100 students from a population in which the true proportion who recycle is 50%. So let's look at our sample. In our sample, 55 said they recycle. So what we're looking for is numbers 55 or more. Since 55 out of 100, we want to estimate the proportion that X was greater than 55%. And so we'll count all the ones that were 55% or higher. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21, 2, 3, 4, 5, 6, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 43. And there were 200 dots. So 43 out of 200. And 43 out of 200 is pretty high. That's going to be actually, what, 21.5%, which is higher than 5%. Remember, 5% is kind of what our threshold is. So this is no. It's not convincing evidence that they recycle. Not convincing evidence that more than half the students at the school would say they recycle, because simulation results show that the proportion of recyclers peaks at 47%. Well, it's not this reason. It's this reason. 43 of the 200 samples yielded a sample portion of at least 55%, and that's higher than 5%. This is the same question, but it has a different sample. The sample is 63 said they recycle. So is this convincing evidence that more than half the students would say they regularly recycle? Same number of dots, but now if you look at 63, that's the only one, right? So only 1 out of 200 dots, which is very, very small, is going to be 63 or higher, which is less than 5%. So it's convincing evidence in this sample. So yes, we have convincing evidence. It's going to be this one right here. There's convincing evidence that more than half the students at the school would say they regularly recycle. Only one of the 200 samples yielded a sample portion of at least 63%. Number 18, you read in a book about bridge that the probability that each of the 4 players is dealt exactly one ace is approximately 11%. What does that mean? If each player gets an ace in only 2 of the first 50 deals, then each player should get an ace in more than 11% of the next 50 deals. That's not true. In 1 million bridge deals, the number of deals on which each player has one ace will be exactly 11% of that. That's not true at all. In a very large number of bridge deals, the percent of deals in which a player has one ace will be very close to 11%. That's pretty good. In every 100 bridge deals, each player has one ace exactly 11 times. Again, that's too precise. That's a no. In a very large number of bridge deals, the average number of aces in a hand will be very close to 11%. That is average number, not percent. That's a percent. So we're going to pick that one because we're talking about percent, and that's a percent. Some of these are kind of common sense. You just got to read through them real clearly. All right, if I toss a fair coin 5 times and the outcomes are tails, 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 then the probability that tails appears in the next toss is 50%. Doesn't matter how many you got. All right, a basketball player claims to make 47% of her shots from the field. We want to simulate the player taking sets of 10 shots, assuming that her claim is true. To simulate the number of makes in 10 shot attempts, you would perform the simulation as follows. Use 10 random 2-digit numbers, 0, 0 to 46. Well, 0, 0, if I list it all out, 0, 0, 0, 1, 0, 2, 0, 3, all the way to 46, that's 47 numbers. So that's all right. We want 0 to 46. This is 48, so that's too much. 47 makes, and then the rest are a miss. Now we're going to simulate the player taking 10 shots. So we're going to use these 2-digit numbers, and then what we'll do is we'll pick 10 numbers from there. And of course I picked the wrong one. It's going to be this one here because we're using 47 numbers, but we're gonna pick 10 of them. So you can see that again right here. I clicked this one. I use 47 2-digit numbers. I'm going to create 47 numbers, but then I'm going to use 10 of them to simulate my 10 shots. So my bad. It's going to be this one right here. All right, number 21, a basketball player claims 47% shots for field. We're going to simulate 10 shots. We're going to have a total of 25 repetitions, so 25 dots on here. The number of makes in each set of 10 simulated shots was recorded. So these are makes. What's the approximate probability that a 47% shooter makes 5 or more shots in 10 attempts? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of, well, there's 25 total, so 12 out of 25. Just count them and make your probability. Same scenario. Suppose the player attempts 10 shots in a game and only makes 3 of them. Does this provide convincing evidence she is less than a 47% shooter? Well, let's see. That's going to be 4. We got to count 3, probability of 3 or less. So the probability of 3 or less is going to be 4 out of 25. Now, 4 out of 25 is what? 16%? And that's higher than 5%. So I would say we don't have convincing evidence that they're less than. It's got to be less than 5%. So it's going to be a no. It's believable she'd make 3 or fewer shots by chance alone. '23, last one. 10% of U.S. households contain 5 or more people. You want to simulate choosing a household at random and recording yes if it contains 5 or more people. Which of these is a correct assignment of digits for this simulation? Let's see, 10% is your probability. So we want to simulate the probability of getting 10%. That means we'd want one of them to be yes, 5 or more. Then the other ones being no, less than 5. So that's where the yeses and no comes. So the 5 just means in the context of your question, like we have 5 or more people in your household. So that's a yes to that survey. But we're going to simulate 10%. So if we're simulating 10%, this is a simulating 50%. Odds and evens is that's no. So it's not that one. That's 5, 5, 6, 7, 8, 9. That's also a 50% simulation. So that's a no. 0, 1, 2, 3, 4, 5. That's 6, 6, 7, 8, 9. So that's a 60% simulation. That's no good at all. This is the only one that's 1, 9, 1 out of 10. That's a 10% simulation. So it's going to be this first one. All right. Hopefully that was helpful for you. Thanks for watching.